Depth charge here for a rather long math tutorial video. Today I'm going to be doing a handout, problems on a handout that cover introductory calculus. And so let's get going. And this date is don't have to worry about that because it doesn't apply for this video. What's important is the problems. All right, what we have here is a limit at infinity, and the input is forever going to the right, increasing to a billion, then a trillion in forever, never ending. And all you do is that you acknowledge that we have an order on top of 3. The highest order on top is 3, the highest order on bottom is 3. So all you do is you make a ratio of lead coefficients. And that is what we call the Y trend. So the answer is A. X trend, Y trend. Here we have the input increasing forever to a billion, a trillion, a quadrillion, and never ending. And it appears that this order is 2 on top, but it's actually 1 because I'm square rooting t squared. So all you do, once again, to determine the output trend of this function is you simply take a ratio, and that's it. This we call the input trend, and this we call the output trend. And that should do it. So C it is. Now in this one, it's actually best to simplify what's inside. Here we have the input going to negative a billion, negative a trillion, negative quadrillion, and on and on and on for forever. So what I recommend we do, because we're going to try not to use a calculator very much in this handout. We're going to use it sometimes, but not very much. And so what we're going to do is we're going to rewrite this limit operation. And this is an operation like any other operation. Square rooting, absolute valuing, this is an operation. Just like that. And rules of exponents, which must be memorized, tell us that we get that right there. Because we've got 2 x's on top, 1 on bottom, and one of them cancels out. So we have to imagine a linear function where x is quote-unquote increasing, negative a billion, negative a trillion, and so on. So what is this? Again, so a calculator can't assist us in this. The function's 5x. Which way are we going? We're scanning to the left. And what does y tend to do? Y tends to increase, quote unquote, negatively. For forever. For forever. And that's what that's an acknowledgement of. So E it is. In AP Calculus, in many calculus courses, you're going to get 5 answer choices, not 4. Next we have a product. Now, again, thought experiments must be done. A calculator can do this. The function is x ln x, which is fine to type in. We have to imagine what that function does as x increases forever. Probably should hit a zoom 6. A zoom 6 allows me to get a standard view, and I trace it to the right. Notice I can't trace to the left because that would be a domain violation, and it just the y output, it just increases for forever. It's pretty straightforward, I think. Infinity is a trend. Underneath's not a number, it's a trend. This next one is tricky because you have to know what secant is. Now, the problem was nice enough to give us a hint. In reality, what this is this. That look good? That looks great. Now, is this a domain violation? Is it a domain violation to input pi sixth in for r? Because if it's not, it's much simpler than if it is a domain violation. Cosine is the function on the denominator, and then it's 2 times the input, which the input is pi sixths. What mode are we in? Oh, by the way, what mode are we in? We're going to be in radian mode, which we are. Pi sixths. Is that a domain violation? No, it's not. Well, that is excellent because I can do a very simple technique of just inputting So that's what I did. I inputted. Notice that the limit operation drops because I'm evaluating the limit by substituting. I believe this is called the substitution method of evaluating a limit. Well, we did the denominator. Good to go. Good to go. 0.5. So this is negative 1 over 0.5. That we should be able to do without a calculator. And that's it. This entire problem should be done without a calculator because it should be memorized what the cosine is of certain inputs. This input right here can be simplified, do the cosine of it, you get 0.5, and then you do the ratio. So, what this means is that the x trend, excuse me, the r trend, which is the input, gets really, really close to pi 6. What does the output trend tend to do? Get really, really close to negative 2. And done. What do we have next? We have another limit as the input gets really, really close to some value. And the most general way of doing this is as follows. The most general way of doing this is you input the function just like that. I type it in correctly. Looks like I did. And you've got your function. And you input, hit the trace button. I could trace it all day long, but I don't hold it down. What I do is I input really, really close to 6, 5.99999. That is on the left side. And what's my output get really close to? 11. Well, I'm not actually done. The answer is 11. But what I should do is I should input not just really, really close on the left side of x equals 6. I should input really, really close on the right side. Now, that is the answer. But what if you have no calculator? What you do is you do this. What two numbers multiply to 30? The answer is 6 and 5. The reason I picked 6 and 5 is because 6 and 5 can add to the middle coefficient, negative and positive. And what cancels out? And what we have is we have this new function where the domain violation has quote-unquote disappeared. And what this allows me to do is neglect the domain violation, which I can't plug in x equals 6. The goal of the substitution method for evaluating limits is to input x equals 6 in this case, which I can't do. But I can do that now. And that's it. 11. This next one's tough because there's no factoring involved. And you can do it the way we did at number 6. You can. There's nothing wrong with doing it the way you did at number 6. However, what if you have no calculator? And the answer is you have to manipulate this with multiplying by what's called a conjugate. So you multiply the function just like that. Notice I'm just taking this function and multiplying it by 1. And then what you do is you distribute. You distribute on top, and I'm not going to distribute on bottom, I'm just going to leave it as is. So what you get is, I'm going to rewrite the limit, which is a pain. X gets really close to 1. The bottom, I'm not going to distribute. Top I am. That times that is and 2 times 2 is, and that can be done because I'm actually foiling. This times this, and that times that, and it just foils out. 3 minus 4 is negative 1. That cancels out. Notice what I'm doing is I'm manipulating this expression into a new expression that's equivalent, and something cancels out. Like I said, this is what you do when you have no calculator. If you have a calculator, you can do, you just punch it in and input really, really close to the input given, and that's it. Now I can input x equal 1. Notice I'm going to drop the limit symbolism. And we get it. What is this? This is actually the square root of 4. 1 plus 3 is 4. This right here is the square root of 4, which is 2. This right here is the square root of 4 plus 2, which is 4. 1/4 is the answer. Unfortunately, that is a choice. Good to go? Good to go. Alright, this is very simple. We have an established trend. This y trend is x gets close to c. This y trend is x gets close to c. This is a property of limits. I'm combining these functions in this way. The answer is actually in the question. So the trend for f is L, the trend for g is k, and you just, right there. The answer is B. And in a later problem, we're going to list out all the properties of limits as the input gets really close to a defined, value like c. It's very straightforward. All right, for this one, let's use the calculator. My input gets really close to 0. 5x on top, sine 4x on bottom. Parentheses, parentheses, parentheses. Very important. And there it is. It looks obnoxious. That's okay, because we're only getting really close to 0. So hit the trace button. What does y get really close to? 1.25. Now again, that's on the left side. That is on the left side of x equals 0. X is never equal to 0. Just like that. 1.25. So the answer is 1.25. Well, where do I get that from the problem? It's actually right here. Again, the way to do this out of a calculator is to memorize, and yes, this should be memorized, this trend right here. That is a very, very important fact to memorize. Right there. Now, it's not the problem. We manipulated this fact to memorize with this 5/4 nonsense, and there it is. All right, next one. Vertical asymptotes. Vertical asymptotes are achieved we have to find an input that produces y equals non-zero divided by 0. Does that happen? Yes. It's very straightforward. This input will produce y equals non-zero over 0, which is undefined. Done and done. All right, so what I'm doing next one. That is a hole. That is a dot. You have to imagine removing what? This dot was removed from the hole. I mean, it wasn't. We have to imagine it. So this is removable discontinuity as a result. This function, it is a function. You're traveling along, and boom. It's a point of discontinuity. Removable. Well, what about the next one? Well, the next one is a little bit different. Move it along, jump! Moving along. That is not removable, that is non-removable. Very straightforward, hopefully. Alright, this next one. This one's tricky because no calculator is going to help you on this one. Now there's a hint here. Right there. Well, what does that mean? What that means is we're going to FOIL this out. And this is not x squared plus h squared. What this is x squared plus 2xh. This is basic foiling and distribution, actually. Distribution is a better name for this. There it is. So what we need to do every single time before we input, the goal is to input h equals 0. That is what we do. We FOIL it out and we simplify. Don't have a lot of room, but I'm going to show a little bit more work. This is going to be done here. That's some more distribution. Look what happens. Look what happens. This completely goes away. We have a new function which allows me, not yet, we'll look at that. 1, 2, 3 terms. What do they all share? This becomes 1, this goes away, and this goes away. What I just did is I changed this into a new function. (6x plus 3h). Awesome. This no longer has a domain violation when h is equal to 0. And what's weird about this is that the answer is in terms of x, because it is. Done. Awesome. All right, next one. Memorize. You got to memorize stuff in calculus and just in life. You got to memorize stuff. That is a very famous function. You can't input x equals 0. When you do this trend analysis, which can be done here, you get 0. Now what am I doing to this function? What I'm doing is I'm multiplying the top by 7. So what I should do is I should show a step. Of factoring out. And there it is. Well, what is this? It's just 0. What I did was I took this trend and multiplied it by 7. 7 times 0 is 0. Next. All right. Continuity has to do with there not being any holes or breaks or vertical asymptotes. Smoothness is not required for there to be continuity. And by the way, can this be factored? Oh, if you can factor, please do. It appears this cancels out, and it really doesn't, because this is the function with the domain violation. That domain violation is right there. Oh, where's a hole? Is there a hole? Yes, there is. You have to know that there's a hole at x equals -1. That is a basic Algebra 2 analysis, pre-cal analysis. Pre-calculus, you've got to acknowledge that when you have it, and this is a domain violation, the domain of this function would be that x cannot equal -1. Now, what is a hole? A hole is an input that produces x equals -1, comma, y equals 0 over 0. Like, that would be true, and it is true. It's a domain violation. This is a bunch of nonsense. 0 over 0 is nonsense. It's a domain violation. But it helps you realize there's a hole right there. That is a place of discontinuity. And it's actually what's called removable discontinuity. So where is there continuity? Well, the answer is everywhere else. Well, where is everywhere else? Everywhere else is here. Well, I give you a hint in this problem about describing intervals. Notice that x can't be 1, which means that x can be negative infinity implies negative billion, negative trillion, negative quadrillion, here, here, and here. Now, the answer is D. Because right here, these parentheses right here, acknowledge that x can't be, the input of the interval cannot be 1. What is this function? Next one. You have to memorize parent functions. You have to do it. And the parent function is y equals root x. Just like that. What are we doing? We are moving, quote unquote, the parent function this way. So where does this function start? So it's right there. Movement to the right. That's literally it. Everywhere this function exists, we have continuity. Do we have continuity at an endpoint? And the answer is yes. Moving on. All right. This has a domain violation right here. And that is that x can't be 0. Now what I'm doing is I'm creating a piecewise function here to take into account the fact that x can't be 0. This problem seems complicated, and it's really not. What this problem is asking you to do is to evaluate a limit. This problem could have been reworded, and it could have asked this. That is literally the problem. Restate it. Factor. Oh, we've got a factor. Just like that. The x's cancel out. So I've simplified it, and the domain violation has quote-unquote disappeared. Can I now input x equals 0? The answer is yes. So that is what the output has to be to quote-unquote fill the hole. This has a hole. This right here has a hole. And the hole is x equals 0. Because that produces y equals 0 over 0, which is impossible. It's a domain violation, but it's also a hole. Now, to account for that hole and to quote-unquote fill it in, we do that. All right, this is a property of limits, and on the next page we're actually going to write out all the properties of limits. And one of them is that if I'm square rooting the function, I can quote-unquote distribute the limit operation like so. Just like that. What is this? This is cubic over cubic. There's a 1 right here. And that's it. That's literally it. 1/2. Can this be in the calculator? Of course. What you do is you put this in the calculator and you scan to the left forever. And the trend, this is actually a horizontal asymptote. This is an acknowledgement of the horizontal asymptote. So, one thing you can say, and these are great questions in all different levels of math. Excuse me. Y equals 1/2 is the horizontal asymptote for That's another analysis of this. It actually all means the same stuff. All right, next. Limit operations are quote-unquote distributive. Here, here, and here. They're not distributive. Distribution is multiplying. So, again, you can punch all this in the calculator, but it's a bunch of, that is some nastiness right there. What you can do is you can quote-unquote distribute the limit operation. So that is an equivalent analysis of this trend as x increases to a billion, a trillion, and for forever to the right. What happens here? Thought experiments. No calculator on this one. Thought experiments. The input increases for forever. The top is 8 and the bottom increases to a billion, a trillion, quadrillion. And what's the trend? This guy's trend would be 0. Plus y equals 2. That's what that means. Y equals 2. What's the input do? Increases to a billion, trillion, quadrillion for forever. What does y tend to do? Stay the same. Here we have a quadratic over a quadratic. That was a joke. On the paper, it's a joke. This is definitely a quadratic. Right there. Squared, squared. And what we're saying is that this top quadratic has a very similar rate of growth to the bottom one. Right there, 10 halves. When I drop this limit symbolism, what I'm saying is that the top grows at a rate 5 times that of the bottom. So this is 2 minus 5, which is negative 3. And like I said in the previous one, if I was to graph this nonsense, which takes a long time to type in, so we're not going to. If I was to graph this nonsense and scan to the right for forever, y would tend to get really, really close to negative 3. That is an acknowledgement of the horizontal asymptote. Moving on. Last page. And properties of limits. General properties of limits. We're going to go with some assumptions here. I'm going to do a lot of writing. Number 20. Here we go. We are going to assume the following. That I have a trend that as x gets really close to c for this function, y gets really close to L. We're also going to assume that as x gets really close to c for another function, g, y gets really close to m. Awesome. So that is an assumption. Now, basic properties. If I analyze the trend as x gets really close to c of the summation of these functions, I can quote-unquote distribute the limit operation. It's not distribution, but you can imagine there's distribution here and there. And I can analyze this trend separately. That is a property of limits. We've got 6 more to go, so I'm going to have to write small. Some difference. Notice that the initial trend is the same for each one. Now what I'm going to do is I'm going to multiply the f function by a constant. K represents a real number. And I can factor out the k. Good to go. Do I have room? Hopefully I do have room for 1, 2, 3, 4 more. It's gonna be tricky. Think I can do it? Give me the product. It's sometimes called the product rule. What I'm about to write. There it is. Good to go. Very little room, but I think we can do it. There it is. What I'm not doing, and I should be doing, but I don't have the room, is that I should be replacing this with M and this with L. So this right here is just, this is L and this is M. I just don't have the room. Two more, which I hopefully have room for. I'm going to raise this function to the n power. Really hard to see here. Hopefully you can see that. Let me zoom in. I'm quote unquote distributing, it's not distribution, I'm quote unquote moving the limit into the inside. There it is. Last one. If I do a trend, it's really close to some input of the square root. This actually works for cube root. Here, let's do nth root. I can quote unquote move it. This quote unquote moves inside. And again, I don't have the room to show it, but this right here, I'm going to show it, is M. So and there it is. These are properties of limits. And there we go. It's all very crystal clear, I hope. All right, two more. We want, what does it say here? We want the domain, which is x intervals, of the graph where it's increasing, decreasing, and neither. This is the neither case, it's flat. But how do you indicate that? Well, what happens is we have these transition points. Right there, that's what's called a vertex. Right there, that's what's called a vertex. The implication here is that the vertex is at x equals 2, or we have a transition from falling to rising. We have a transition here, I don't think that's called a vertex, it could be. Who knows? What I do know is that we have a transition from rising to flatness. So you have to scan this from left to right. Rise, fall, rise, flat. Where is this function rising? When I say rising, I'm talking about the output. Where is the function's output rising? It rises, so it starts, quote unquote, at negative infinity, and it ends at negative 3. It does not rise or fall at negative 3. Good. It also rises from x equals 2, x equals 5. That's it. It's falling from x equals negative 3 to x equals 2. This is what we call begin, comma, end. Not x, comma, y. Is that all it falling? Is that the only place it falls? Yes. Where is it flat? This is a flat output function starting at x equals 5 to forever. And that's it. This is quote unquote end. This is quote unquote beginning. Pretty straightforward, I hope. Last one of the day. We have a function here. And you can be asked all sorts of questions about these functions. This is all concepts, very little calculator, no calculator that can be done. This function falls, it jumps, falls, rises, has a whole point of discontinuity, and it rises again. There are two spots of discontinuity. This is what we call non-removable discontinuity. This is what we call removable discontinuity. All right, what happens on the left side? What happens on the left side, this is where we have to imagine time flowing left. And what happens, this A is simply an acknowledgement of that right there, end behavior. And that is it. Straightforward, I hope. This right here is you have to imagine x getting really, really close to the input of negative 4 without getting there from the left. This means from the left, which also means that there's movement to the right. You have to imagine moving down this hill, and what does y get really, really close to? Well, it would get really close to something if there was an actual value. What is missing from this graph is so let's put negative 3 right there. That's what should have been there, but now it's fixed. So y is going to get really, really close to negative 3. And there it is. What happens here? You have to imagine movement from the right toward x getting really, really close to negative 4. And what does y get really, really close to? Basically, you are looking right there. Right there. And that's it. Now, what you see here, basically the reason I asked B and C before D is that you have to look at D. D is actually two problems in one. And those two problems for D are B and C. There's an inconsistency right here. Inconsistency. D, N, E. Does not exist. This is input 0. What is the output? This is actually an Algebra 1 or Algebra 2 question. Right here. X equals 0 is right there. Very straightforward, I hope. On to F. This is actually two problems. You have to analyze two things at once. You have to imagine x getting really, really close to 0 from the left and from the right, and you have a consistency. 0 it is. This is a coincidence that they're the same. They're not always the same. All right, 4 from the left. Movement, movement, movement. Y gets really close to 2. Notice these answers are literally just read off of a graph. From the right, 4. X gets really, really close to 4. You have to imagine right here, that right there, means this right here. Move, 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 move. Get really, really close. We never get there. What does y get really close to? 2. Do we have this consistency? These two problems are I, part I. They're the same. Done and done. What do we call this? We call this end behavior right there. What does y tend to do? Grow for forever. Last one. This is an Algebra 1 or Algebra 2 question. Input 4. What's the output? Is it here? No, that's a hole. -3. Notice that the trend, as x gets really, really close to 4, is 2. Right there. And right there, and right there. But the actual output at x equals 4 is not 2. It's some other value, which I had failed to write, but I fixed it. Hope you enjoyed this video. Please hit the thumbs up, share, and consider subscribing. And please be kind in these uncertain times. Depth charge out.